Okay, let's look at important topic in graphics, which is scalar field visualization. So just share my screen. Okay. So what we have is we have a 1D data, and we have to see how we can visualize this data and get some geometry out of the data. And let's look at 1D data first. So let's look at what is the definition of a scalar field. A scalar field is a function from a domain. It's a real valued function from D to R, and a scalar field is mapped to every point of a given domain. So with every point in the particular domain, we are associating a corresponding real value. Some of the examples of scalar fields are temperature, pressure, uh, density, etc. So we are familiar with function plots. What we do is we have samples of the data points, and correspondingly, according to a particular data domain point, we have the corresponding real value. And I mean, these values are actually could be connected by a linear, like piecewise linear functions or even curves. Okay. Now let's look at the 2D scalar field visualization. So here we have three options. One is we can do a function plot, which is from, so this function plot will be a three-dimensional representation because two axes will be actually used for the domain. So the function is from R squared to R. Two axes will be used for domain, and third will be for the plot value. Another way of representing scalar field is using by assigning colors for different values of different scalar values. So here you can use some kind of a color grade. For lower values, you give a particular color, and for higher values, you give another color. That is one way of representing it. Another very popular way of doing this, and which is an important way of representing 2D, is something known as contour plots. In contour plots, what we do is we find the locus of all points, which gives an pre-image of a particular scalar value. For example, if C is a scalar value, we find inverse of C, which in turn gives you a set of all points which has value C, and you plot them. Then you get a corresponding contour of that particular scalar value. So these three methods are actually can be employed for visualizing 2D. Let's move to 3D. 3D, the first method where we were using function plots, then here will require the function is from R3 to R. So you'll require three axes for the domain and one axis for the function value. So that will be a four-dimensional thing, which is not possible to represent. Or even a more precise way of representing the function is it's mostly we use unit cube as the domain. So it's from I3 to R. But in that case also it's not possible to represent the 4D thing. So what we can do is we can do something like a volume slicing technique. So what we do in volume slicing is we restrict the domain of the function into 2D by we restrict it to a subdomain like D dash. And if the D dash is a 2D object, then we eventually have a 2D scalar field. And for a 2D scalar field, we actually know how to represent it. So in this image, you'll see a plane which is actually sliced through the viewing volume. And since the plane is a 2D object, you get a corresponding 2D scalar field out of it, and you have standard methods of visualizing 2D fields out of that. So there are multiple ways you can actually do the slicing. You can do axis parallel slicing, where you slice parallel to the three coordinate axes which we have here. Or you can even slice it along some arbitrary direction, which is also then in the axis parallel case, we already have the data points which are available to us. Then if you're doing a non-axis parallel slicing, then you have to interpolate the function values at the arbitrary points. Also, the points also you have to interpret using some linear or binary interpolation technique. This is also like a way to explain slicing in uh, 2D. So if you have a function which is from R squared to R, which is a 2D scalar field representation, to understand slicing, we can look at a 1D slicing of this. So what we do is, let's look at something like an axis parallel slicing. So we look at a line which is actually parallel to one of the axes. Uh, then you have already the grid points, the sample points along that particular line, and you know the corresponding scalar values for these lines, and you can plot the uh, 1D function. Similarly, if you have to move along the line, you can shift the axis parallel line, and if you want a point in between, then those points can be linearly interpolated between these two values as well. This is how we do for a 2D. Instead of a line, you have a plane, and instead of a point sample, you have grids, 2D grids, and you'll be looking plotting the function for each grid. So that's how slicing works. Okay. And one of the most important way of obtaining a scalar field visualization is something which is known as isosurface extraction, which is actually isocontour extraction, which we have discussed in 2D. So what we do is we find the preimage of the function with respect to some scalar value c, which eventually belongs to R3, and the set of all such points will give you isosurface. So depending on the kind of object which you're interested in, the ISO values can vary. The C value can actually vary. So in this image, you see something like MRI data, and using isosurface extraction of this MRI data, you can actually get either the skin of the person for lower ISO values and the skeleton of the bones of the person for higher ISO values. This is the very popular way of getting isosurfaces. 3D visualizations. Okay. So we'll look this isosurfacing in more detail in the next lecture. Let's conclude this lecture now.